So the first thing I want you guys to know about integrals is that they are antiderivatives, or that the process of finding an integral is the inverse process of taking a derivative. Okay, so just to state that a little bit more precisely and introduce some notation here, this curly symbol that I just drew, that's the integral sign. So the integral of f of x with respect to x. And let me even be more clear. The integral of lowercase f is equal to uppercase f of x. I'm using this uppercase, lowercase notation is something you'll see in lots of books. That's part of why I'm using it. What that is saying, it's exactly the same thing as saying that the derivative of uppercase f is lowercase f. Okay. So the integral is the process that undoes taking the derivative. If we start with f, we get to little f. We start with capital F, we get to lowercase f by taking the derivative here. If we want to get back to uppercase f, we take the integral of the derivative. Okay, so another way to put that together is the integral of the derivative is the function itself. The derivative of the integral is the function itself. So it's kind of the same basic relationship that applies to exponentials and logs. The difference is you take the exponential, or you raise e to the power, or take the log of a number, and taking derivatives and finding integrals, those are things you do to a function. So they have the same get you back to where you started from relationship, but you're performing them on functions, and what we're getting is a function. So that makes them a little bit more complicated. Okay, so a thing to bear in mind throughout this unit on integration is, first thing is, integrals are really important. They are really important in probability. We're going to be using integrals in 200A. You're going to use them in every methods class you take. I bet. They're the foundation of probability theory. That's the foundation for statistics. So you do need to be comfortable with the idea of an integral, with working with them, with decoding statements involving them. Okay, so that's on the one hand why you should pay attention to this stuff. On the other hand, the process that I'm going to talk about in the rest of this video, like for a specific function, finding its integral, you're almost never going to do that. Okay, so integration is something where we don't do it that often. Computers usually do it for us when it needs to be done. So I'm going to try and take a balanced approach to finding integrals. I want you to be able to do a little bit of it because that will help you make the abstract concepts more concrete. It'll help you wrap your brain around the whole thing. But I'm less concerned with you being able to actually evaluate integrals than I am with you being able to understand the idea. Okay, that said, with that little intro, let's talk about how you might actually evaluate an integral. Get my pen back here. So say we had a nice simple integral. Find the integral of x squared with respect to x. For our purposes, the approach to this kind of finding an integral is kind of a guess and check process. Think about, how can I reverse engineer the process of taking a derivative to find something whose derivative would look like x squared. Okay. Well, we can kind of think about how that would work. We know that with powers of x, when you take derivatives, the powers get smaller and smaller. And so the derivative, a function that has a derivative, x squared, is probably going to have x cubed. And that would seem to make sense. Let's think about what the derivative of x cubed is, though. It's 3x squared. Okay, it's not exactly what I'm looking for. We've got this 3 here. That's annoying. What I want is just plain x squared. So first guess didn't go exactly as I wanted it to, but let's try another guess. Okay. I liked the x cubed because it gave me the right exponent on my derivative function. I just want to get rid of that 3 here, the 3 that's multiplying the x squared. Well, how about if I divide out by it? Okay, so if I have a function x cubed divided by 3 and I take its derivative, I've got that 1/3, there's 3, and then I have 3x squared, the 3 and the 1/3 cancel out. How nice, and I'm left with x squared. That's the answer here. What is the function whose derivative is x squared? It is x cubed over 3. Okay. And so that really, the integrals you are going to need to evaluate, you can do it this way, just by sort of backward reasoning through the process of taking derivatives. So that is true. The derivative of x cubed over 3 is x squared, but you might be thinking, so is the derivative of x cubed plus 5, okay? It's also x squared, or x cubed over 3 minus 11, or any constant added to that x cubed. So here I'm using c just to represent any number. Doesn't have to be an integer, it doesn't have to be positive, it can be any real number here. And because that constant here is appearing by itself, its derivative will be 0, we lose that information when we take the derivative of a function. And so we get it back to some extent, or we remind ourselves at least that there's something that we're not getting back when we add plus c. So this is my final answer. Taking the integral of x squared is finding the function whose derivative is x squared. And the answer to that is a family of functions. They all have x cubed over 3 in them, and they just differ by the value of this constant that would get lost when we take derivatives. Okay. So what we have here, that is the answer to the integral of x squared here, and we call that an indefinite integral. Okay, and the indefinite thing is this plus c business here. Definite integrals are also a thing, and we're going to talk about them next. But what I want to do first is just talk a little bit about finding some integrals. And again, this is the part of the lesson that I was trying to give that nuanced message for. Spend a little bit of time with this. It's not that hard. It will help you be able to work through some examples to make some very abstract concepts a little more concrete. That said, don't think that you're going to need to be taking the integrals of lots and lots of functions outside of learning other things. Okay, so the rules for finding integrals are rules to help you follow examples that will be designed to teach you other things that are directly useful. Okay, so the rules for integrals. So there is a power rule here. So we saw like an example of this with the integral of x squared. So what if we just have the integral of x to any arbitrary power here? So the integral of x raised to the power a, what is that? That is x raised to the next higher power, again, because we're undoing the differentiation process. Let me make that 1 a little bit clearer here. So a plus 1 divided by a plus 1, and then I have that constant of integration. Okay, so the integral of x cubed would be x to the 4th over 4. The integral of x to the 4th power would be x to the 5th over 5. It's that kind of rule. The same rule applies to negative exponents. It applies to fractional exponents, just like we found with the power rule. Okay, so that's how to take the integral of any function involving a power of x. Well, what about when x is in the power? So we have an exponential rule here. If we have a function e to the ax power and we want to take its integral, that is the same thing. Okay, that's the deal with when we take derivatives of e, or e raised to a function, we keep that same function in the power, but then we have a chain rule that we're correcting for here. So it's e to the ax plus c. Okay. And again, you can check all these rules. Just take the derivative of e to the ax over a, and it will be the 1 over a constant, the a from the chain rule, the derivative of the inside, times e to the ax. The a's will cancel out, and you'll get back the function that you started. We have a rule for constant multiplication. That tells us that the integral of k is another constant here, times f of x dx is equal to k times the integral of the function. So we can pull constants outside of the integral here. And switching color for a minute, that actually tells us something about the integral of a constant. Okay, so we just say we have not a function here, or a kind of a degenerate function, the function that always equals k. Let's rewrite that as the integral of k times x to the 0 power, so 0 dx. So I'm going to put together the constant multiplication rule and the power rule. Constant multiplication rule says that I can pull the k outside, and the power rule says I'm just left with this x to the 0 power. So what I've got is x to the 0 plus 1, that's 1, divided by 0 plus 1, that's also 1. I get kx. And again, like, did we really need calculus to say that the function whose derivative, that is, whose slope is a constant, is a linear function? No, we knew that already, but it's really nice to see how something that we already knew fits into this much broader framework. Okay, what else do we have? Oh, we have an addition rule. If I want the integral of the sum of f of x plus g of x, that whole thing with respect to x, that is equal to the sum of the integrals. It's one of the nice rules that we have. G of x dx. So that's great. There's no general rule for the integral of a product. Some of you guys who have a good calculus background, you might have spent some time learning some kind of fancy integration techniques, integration by parts, integration by substitution, things that are techniques for looking at a function and kind of seeing the product rule lurking there or the chain rule lurking there. That's more than you need for the uses of integrals that we're going to be requiring. Okay, I got one more thing to add to the rules here. It's kind of the hole in the power rule, so to speak. There is no function, no polynomial function, no power function that gives us 1 over x as a derivative, but we might want to think about what the derivative of the integral of 1 over x is. Okay, so just saying what I said a minute ago, maybe a little bit more clearly. There is no power of x function that will give x to the -1 power as its derivative, but there's another function, right? Okay, so the derivative of log x is 1 over x, but there's always that caveat that we have with log functions. They're only defined for x greater than 0. Okay, so that's something, and maybe that's all we had, it would still be something, but we actually have something more, okay? Because the log of negative x is defined for x less than 0. Okay, right? If x is less than 0, then negative x is positive, so we can take its log, and we can find the derivative of that using the chain rule. So let's just do our chain rule thing here, the derivative of the log of negative x, keep my negative there. Okay, well, it is 1 over the thing I'm taking a log of, that's the negative x, but I have to do the derivative of the inside as well. This is the derivative of the outside, the derivative of the log thing. The derivative of the thing I'm taking a log of is negative 1. And look at that. So when x is less than 0, I just said negative x is greater than 0. Okay, and what this means is negative x is the absolute value of x. And when x is greater than 0, just plain x is the absolute value of x. So that gives us our answer here. This is all kind of my work here. My answer is this is the log of the absolute value of x plus a constant. Okay, so that's maybe a little less versatile than the other rules, but that is a fact that might help you again work through these concrete examples. Okay, so this is enough for you to kind of get going with actually finding the integrals of some specific functions. In the next video, we're not going to be talking a lot about computation or really even a lot of things you guys will be doing as problems, but I want to talk about sort of the big picture of integrals. So I'll see you then.